Good afternoon, everyone. Today we're going to look at a limit that at first glance looks like it might not exist, but with a bit of algebra, we see that we can get a nice value for it. So we're looking at the limit of x as it goes to -4 of x squared minus 16 all over x squared plus 6x plus 8, a classic rational function, which is perhaps something that you studied recently if you're in Nova Scotia. So what we can do first is notice that if we do plug in x being -4 right into the function, what we'll find is we'll replace the x with by -4. So we'll have -4 squared minus 16 all over -4 squared plus 6 times -4 plus 8. And we're going to run into some trouble because -4 squared is 16, so in the numerator we have 16 minus 16, all over 16 minus 24 plus 8, and so we get a classic indeterminate form, meaning a 0 over 0. We could also have an infinity over infinity, but in this case we have an indeterminate form of 0 over 0. So, at first glance the limit might look like it doesn't exist, but if you remember how to work with rational functions, you might remember that we can factor both the top and bottom. So if we go ahead and do that, you'll notice that this is really the limit as x goes to -4 of difference of squares, means we can factor as x plus 4, x minus 4, and all over any easy trinomial that factors as x plus 4, x plus 2. And now, right, we see that they have a common factor of x plus 4, and so we can get rid of it, cancel it out, right? You know that this would really produce a point of discontinuity, right? On a graph of a rational function, we would see a P.O.D. at x is equal to -4, but it would be a singular point of discontinuity on the graph. The function, as x approaches -4 from both sides, would still tend to get right up to that value, infinitesimally close to it, okay? So we can still evaluate the limit because it would exist on both sides of the -4. Smack dab at -4, it's a point of discontinuity, but again, limits are as x approaches the value of -4 from both directions, not at the actual value, right? These are the subtleties of limits. And so if we go ahead and go through with our tiny bit of algebra, we notice that we can now evaluate the limit as x goes to -4 of what's left, because that is simply plugging in -4 for x gives us -4 minus 4 all over -4 plus 2, which is -8 all over -2, which is 4, okay? So if you wanted to check on Desmos, you could plot this function and notice, or on any graphing software, you notice that you have a point of discontinuity, a P.O.D. at x is equal to -4 and y is equal to 4, okay? So again, we have a point of discontinuity, but again, because of the way the limits are defined, that is from both directions closing in and in and in to that one specific value without actually having to be defined at that specific value itself. A point of discontinuity does not mean that the limit does not exist, okay? The limit exists, namely, it is 4. So, hope that helps. Thanks for watching. Take care.